Hello everyone, and welcome to part 2 of the 4.2 notes where we're talking about exponential functions. I want to start out this discussion since we're about to look at some applications of exponential functions. There's a number that's called e, and I'm not sure if you're familiar with it, but this number e, it is approximately 2.72, kind of like how we say that the number pi is approximately equal to 3.14. It's an irrational number, and so this number, it has a repeating decimal that repeats forever, and actually it never duplicates any kind of a pattern or anything, so that's a general idea of what it means to be an irrational number. But this number e, it's used a lot of times when we're dealing with exponents and logarithms because of a similarity that it has. Especially, we will talk somewhat about the relationship between these two formulas that we see here. In general, we're about to take a look at a couple of applications of exponential functions, and one of the applications that comes to mind right away is using them for calculating interest, because of course when you have interest, and in particular when we have compound interest as opposed to simple interest, compound interest is something that grows exponentially. We have these ideas of exponential growth, which this is what occurs whenever that number b that we saw, which is the base, when you have a function that goes a times b to the x, whenever this b is more than 1, that's the case when you have exponential growth. And then whenever that b is less than 1, it's one of the numbers that's in between 0 and 1, because we said there's also that possibility. It's called exponential decay. And so that's whenever this b over here is in between 0 and 1. And a bank account is something, either a bank account or whatever is accruing interest. It could be, a loan or something like that, is going to grow exponentially. And so, since we deal with exponents, especially whenever we have a formula like this, I want to show you that there are many different representations for the number e, but there is a way to represent this number which uses the idea of a limit. And not to get too much into the idea of what a limit is, but this is the limit, the way you would pronounce this symbol over here, the limit as n approaches infinity. So basically we're about to have a formula that has n in there, and this means what number are we getting close to whenever the value n is just getting bigger and bigger and bigger. And if we put here 1 plus 1 over n, and then we go to the n power, and we just let this number n get as big as possible, and of course these numbers are the same, so if we plug in 2, it would go 1 plus 1/2 and then squared. If we just keep plugging in numbers for n that just get larger and larger and larger, going all the way up to infinity, this actually will be equal to the number e. And so what you can see here is that this formula for compound interest, it basically has that format. It goes 1 plus something over n, and then it goes to the power that has n in there. And so it's almost the same as what we have here, and this is actually why when we do compound interest, if there's a finite number of compounding periods, for example, you might have annually, which means once per year. You could have something like monthly, which means 12 times per year, etc. These kinds of compounding periods, it's possible for them to be a finite number like 1 or 12, or maybe quarterly would be 4. It's also possible to have this idea of continuous compounding where the number of compounding periods actually is infinite. There's not a way to say which number of periods there are, and so that's why when we have this kind of infinite period, this number n here and the exponent over here are both going to infinity, and that's what, when this thing goes to infinity, we get the number e, and that's basically how it works out, why this equation has this e over here. But anyways, if we want to just do some calculations, we should plug things into the formula. And just a couple of notes about how things will get plugged into the formula. The p over here in this formula is called the principal, so that's the original amount. And then there's an interest rate, which the interest rate that's given in a problem like this, it's called the nominal rate, where nominal basically means just the name. because this rate is only going to be the name of a rate. Basically, the rate of interest that you actually get, which you could call maybe the annual percentage rate, which is like APR or whatever. You might hear that on a car commercial where they're talking about taking out loans. That is the true rate that you're getting, the APR. This thing, the nominal rate, it's only there to represent the rate, because the rate also depends on how many periods there are per year. And so I don't want to go off on much of a tangent with that one, but what I mean to say is that if here, for example, with this problem number 9, it says that there's a 2.5% interest rate, it has different compounding options that we're looking at, either compounded annually, compounded continuously, or compounded quarterly, these kinds of things. The true interest rate that you have after 1 year will depend on the number of periods. And so the more periods that you have, the higher the actual rate will be. So compounded annually, you actually will get 2.5% every year. Compounded quarterly, you'll get actually slightly more than 2.5%. And then compounded continuously, you'll get even more of a interest rate than that. But anyway, we just want to try plugging in these values into some of these formulas. Here, when we say A on this one, this means the compounded amount. So it is the original amount, which is the principal, and then plus any kind of an interest added on top of that one. And so here, the original amount is $15,000. And then we're going to have compounded annually. So that means that this number N is just 1. This interest rate that's given, that's always the R, so it's 0.025. We should put it as a decimal, 2.5% of the decimal there. And then it's for 7 years. So the number of years is the T over here. And now we're ready to plug everything in. So it should go the principal, which is 15,000. I should signify that's the P there. And then we go times 1 plus the interest rate divided by the number of periods. And so in this case, the number of periods are just 1 because it's annual. And then we go to the exponent that is the number of periods per year times the number of years. So basically the number that ends up as the exponent is the total number of periods that have occurred, which is 1 times 7 there. So this would go basically 15,000 times, we can add these for the first step, we can just divide anything by 1, it's just itself. So this goes 1.025 when we add these, and then it goes to the 7th power. You will get some number for this one. And then we can do the same thing compounded quarterly. The only thing that's going to change is that in this case N is equal to 4 because that's the number of periods per year. Now compounded continuously, it's slightly different as well. We're actually going to use a different formula for this one. We're using the one that goes A equals P times e to the RT power. And we have the same R from before, goes 0.025. We have the same T, which is the 7 years. And then the principal is 15,000. And of course E, this is a button on your calculator because it represents that number that is a little bit less than 3. And you would be able to calculate this one. So that does it for this example about exponential growth. We will see one more example where we're dealing with exponential decay, and then we will be done with 4.2. And so thank you guys for hanging in there with this video, and I'll catch you in the next one.